Okay, good afternoon, everyone. So we're going to start a new unit today on principal components analysis. This will be the first unit on unsupervised learning. So basically, the motivation is what we call dimensionality reduction. The idea is that many modern data sets have very high dimension D, so the number of features can be very large. And we would like to know if we can somehow reduce the dimensionality if possible without losing too much information. The reason we might want to do this is because maybe we can simplify downstream tasks like classification or regression, or maybe we just want to save memory or storage space, or maybe we want to visualize the structure in the data. Like if we can reduce the features down to 2 dimensions, we can plot them like as a scatter plot, and we can understand what's going on better. So there's many different ways to do this. We're going to look at the simplest way to do this, the most classical way, which is called PCA, Principal Components Analysis. And basically, this is a linear technique, but it's RSS optimal. So when you put linearity and RSS optimality together, you get things that are tractable, things that you can derive in closed form. We saw that back when we did linear regression. We were able to, find the optimal linear estimator in closed form. Now we can do this with PCA, optimal linear dimensionality reducer. Towards the end, we'll also just briefly describe a couple modern nonlinear tools, just so you know about them. And they can be useful when you're trying to visualize data sets or get a new data set and try to understand it. You can use those for the project if you find them helpful. Okay, so basically now our data set is just the x's. There's no more y's. There's no more targets or labels. And as always, each of our x vectors has d elements. Dimensionality is d. And as always, we collect n of these things together, and we can stack them as rows of a matrix if we want. And we are going to assume throughout this whole unit that the data has been centered, meaning the mean was removed. This is always something we can easily do, and it just makes a lot of the math a lot easier. So we're just going to assume this throughout. So again, there's no targets, no labels here, there's no y's. Maybe they exist, but we're going to ignore them for now. And this is known as unsupervised learning, in contrast to what we've done before with supervised learning, where you have features and labels and you try to predict the label from the feature. You try to design some system that does that, for example, classification or regression. But we're doing something different now. We don't have any labels. And so the main question again is, what can we do if the data dimension D is very large? Is there some way we can reduce the dimension without losing too much information to help with further data processing? Okay, so we're going to, just as our demo, we're going to use some face data. This data set is not really very new. It's from 2007, and it's not a very sophisticated data set in that the faces are still pretty small, 1,850 pixels. So that's not really super big, right? As images, 50 by 37 images are pretty small. Modern face data sets can have like 1 million pixels per image. So we could do that in practice too. It would just, things take longer to run in that case. So we're just gonna work with this data set. And there's another nice thing about this data set is that it does have labels. It's labeled by the different people that are represented. They're mainly some politicians and so on. We'll see. But because we have labels, we can do an experiment like, what if we do PCA to reduce dimensionality, and then we try to do classification after we've reduced dimensionality? Does this hurt us a lot or not? So we can do that experiment because this database actually does have labels. But we're not going to use the labels to do the data compression. Essentially, that's really what we're doing. We're doing data compression, a simple form of data compression. So this is a pretty well-known data set. It's built into sklearn. There's a total of 13,000 images. These are from news stories in the 2000s, so you have people like Donald Rumsfeld, Colin Powell, George Bush, Gerhard Schroeder, and here you can see examples of these images, 50 by 37. They're just high enough resolution that you can see who these people are, but certainly not super high quality. And we're going to require when we download the data to use faces from people where there's at least 70 faces of those people in the data set. So that's going to reduce us to 1,288 images, and there's 7 total classes, or there's 7 people that have that many faces each. Okay, so, all right, so that's kind of the setup for what we're going to do later with the demo. But unfortunately, we have a bunch of math to do before we get to the fun stuff, playing with the demo and looking at pictures. So today is going to be a lot of linear algebra, as you're going to see. Okay, so if we summarize what we want to do, this is probably, in some sense, the most important part, is just understanding what we want to do. We want to do a linear approximation of each one of these feature vectors. So in other words, like each face, we want to linearly approximate it as follows. So let me try to draw this. So if I take that face image and I flatten it into one long vector of, 1850 pixels, what we're saying is that we're going to try to approximate this by the product of a matrix, a tall matrix, and a short vector. So this has dimension d. This vector here is dimension r. R should be much less than d. Okay, so hopefully you can see how this matrix times this vector is something of this dimension, but essentially we're coding that particular face with just r numbers. So to get back that face, I need these r numbers, and then we also have this fixed matrix, which we call B, we're going to learn it for this entire data set. Okay, so we can think of this B as like a dictionary matrix with r columns or r elements in the dictionary. Z contains r coefficients that we will use to linearly combine the dictionary elements. And we're going to do that separate zi for each image I. And so therefore, b times zi is a linear approximation of xi. It's a linear because the function taking us from zi to xi is linear. You can definitely do this better if you allow yourself a nonlinear function. For example, you could use a deep neural network or something. But you can't derive anything in that case. So we're doing this because it's simple, because it's really classical, and we can derive everything. You can see exactly what happens. And this number r is called the rank of the approximation. So we want r to be much less than the original feature dimension, because if not, it's not really worth doing all this, right? We're really trying to compress. And if we can compress a lot, then maybe it's worthwhile. So we'll see how much we can compress these faces later. Okay, so are there questions on this overall approach? Yeah.
If we're training a different ZI for each image, how do we kind of expand that to do something on data that it wasn't trained on?
So, so in some sense, the information that you have over all faces is contained in this B matrix. And so that's kind of the global information about the data set. And then it's sort of saying, like, to construct different faces, you have just different short zi vectors that can get you these faces. So it's still, I mean, you raise a good question. In some sense, right now we're not trying to we're not trying to do something with data that we haven't seen. But this B matrix we're learning has sort of the structure that should apply to any face that is similar to the faces we've seen.
So the B is like what we're doing to approximate different faces, and then the Z is what defines each different one? Like each
That's right, yeah. We could do something like this. We're not going to do this, but let's say that you have this face data, all these XIs, and let's say we've computed for all our XIs a good B and a good ZI. You could then do something where you look at all these ZIs, and maybe you do something like try to approximate them by a multivariate Gaussian distribution. And then what you do to generate a new face is you randomly generate a Gaussian vector from that distribution, and then you put it through B, and out pops a new face. That would be what's called a generative model, or a very simple one. And that is something you could do. It's not really very typical with PCA, but it's something you could do, like you're saying, if you want to generalize this beyond the data that you have. Yeah. Okay, good question. Yes?
Could you remind me what the difference between ZI, and I know we don't have a YI in this case, it's unsupervised, but like what a YI usually is?
The difference between ZI and
And YI.
O. So YI is usually a target. We're trying to, you're given like input-output pairs. It's kind of like you're trying to train a system where if given an input, it can predict what the output will be. Here we have no outputs. We just have like a bunch of inputs. And we're essentially saying like, can we compress those inputs? Can we come up with a representation of them that takes up less storage?
Okay.
Yeah. So it's very similar to like, JPEG or MPEG or all these things you do for images or video or audio, MP3, except it's simple in that it's just a linear method. All those other things I just mentioned are complicated nonlinear approaches to compression.
Okay.
But they're all similar in that they're all lossy compression. You lose something when you compress. It's not like zipping a file where you lose nothing. MP3, JPEG, all those methods, like you lose information, but what you get out does not look quite as good as what you started with. And that's the same thing here, is that this approximation is not exactly this. So you do lose something. Okay. And how much you lose is controlled by this R. Like the smaller R gets, the less, the more crude your dictionary is, the less information you're storing in any ZI, and therefore the approximation will get worse and worse as you reduce R. Okay. All right. Any other questions? Okay. All right. So that's what we want to do is we want to design B and ZI for all the different I to match our XIs. Now, how do we do that exactly? We're going to minimize RSS, just similar to what we did back in Unit 2. So we have the sum over all our data samples of the error between xi and our approximation, sum squared error. Okay. The difference now is we are designing the matrix B, and we're designing all these individual vectors zi so that we can together get as close as possible to our xi's. So this is the definition of principal component analysis. We're using RSS for simplicity. Maybe you would say, what if I want to do mean absolute error? Wouldn't that work better in some cases? Well, unfortunately, even if it would work better, you can't really derive anything in that case. So the combination between linearity and the 2 norm gives us tractable solutions where we can actually derive stuff. We do have to be careful, and I'll show you an example later. If you do this, if you choose this approximation criteria, you may throw out information that's super important to you because that information might not be important to this, but it might be important to something else like classification. So it could be that like to classify, one person's face versus another person's face, you have to look at very small details, which PCA will think is not that important. I'm just going to throw them out because it doesn't affect my square that much, but maybe it affects your classifier a lot. So we'll talk about that a little bit, but it's just important to note that this is chosen for simplicity, not because it's like the right thing to do with classification or some other downstream task. Okay, so any questions on our objective? Making sense? Okay. So here's a summary of what the solution is, and then we'll do the derivation later to get to these equations. So it turns out that the optimal dictionary, the one that solves this problem, we'll call that B hat. This is a matrix VR whose columns v1, little v1 through little vr, are the eigenvectors corresponding to our largest eigenvalues of the sample covariance matrix. So the sample covariance matrix is this. So we talked about sample covariance way back in lecture 2. So this is like column times row. So each one of these is a matrix. It's a rank 1 matrix, but then when you average them, you build up the full covariance matrix. Now, in case you're wondering why are we not subtracting the mean before we do this multiplication, it's because we already subtracted the mean when we assumed that xi are centered. So we took the sample mean, we computed the sample mean across all of our features, we subtracted that from all of our data, and now the sample mean of the result is exactly 0. So we don't need to subtract it out to compute the sample covariance matrix. Okay, so this is how this sample covariance matrix Q is defined. And if you do an eigenvalue decomposition, that means you can write that matrix in this form. These are vectors V, or vector V and its transpose. Those are what you call the eigenvector. These lambda j's are scalars, turn out to be positive scalars, or non-negative scalars. These are the eigenvalues. So we'll talk more about this in a moment, but I think you guys have all seen eigenvalue decompositions at some point in the past when you took a linear algebra course. How many people, has anybody not seen them? I'm just curious. Okay, great. So this is the optimal dictionary. Basically, you take your data, you compute the sample covariance matrix, you do the eigen decomposition, you end up getting d different eigenvalues and eigenvectors. You look through them to find which are the ones that correspond to the largest eigenvalues, our largest ones, and you keep those eigenvectors, you stack them in a matrix, and that becomes your optimal dictionary. Then, in order to get those optimal coefficient vectors zi, these are these short little vectors, you take your original data samples and you multiply them by that same matrix transpose, and that will give you the little zi's. And together those zi hats and this b hat give you they are the ones that minimize this RSS. So let's look at a couple pictures. So this is, picture on the left here is if my data has 3 dimensions originally, and this says I want to squeeze it down to 2 dimensions. So the data is given by these dots, which are here illustrated in 3 space. Of course, we're only able to, plot a 2-dimensional projection of this 3 space, but you can kind of imagine that those points are in 3 space. And if you looked at that cloud of data, you would look to see which directions is it widest in these 3 dimensions. And it's going to be wide in this dimension, and that's how it's widest in that dimension, and it's second widest in that dimension. And then there's one more dimension orthogonal to those where it's the least wide. So what PCA does is it says, take the 2 widest dimensions, since we're approximating it by rank 2, and project all those points into the plane that's defined by those 2 dimensions. And so all the points in that plane essentially are the ones that you can create with this PCA with rank 2. And the approximation error you get are these are the errors you get for each data point. So some of them are very close to being on the plane, some of them are farther. But that's what you lose when you do PCA. Now you might say, actually, I want to do PCA with one dimension. So in that case, you just look for the single dimension within this three-dimensional data cloud where you have the largest variance, and that's going to be along this dimension, and that is your approximation. And so now you're saying, I'm going to approximate my entire data set by points along this line. And now these are the approximation errors you get. Obviously, this approximation is worse than this one. That's the cost of decreasing your rank. You get more data compression, but bigger errors. Okay, questions? So, do you remember seeing plots that were sort of similar to this back in lecture 2? Okay, what was the difference between those plots and these plots? There's sort of an important difference. Do you remember, what were those plots? What were we plotting? What was on this axis in those plots? So the features, let's say, were on those axes. What was on this axis in regression? Not the error. The targets. So this was like y, and this was like x1 and x2. Okay. And when we did that, do you remember these little stems? Which way were they pointing? Were they pointing this way, or were they pointing a different way? What kind of error did we care about in that case? Error in the vertical only, right? So in that case, all these stems were up and down because we cared about error in the y domain, in our predicted domain. So that's the difference here. The stems are not, according to some targets. We don't have any targets. So it's all about the data. We have x1, x2, x3, and we have an approximation of our data, which is anything in this plane we can create with PCA. Anything outside the plane, we can't. So the error is defined by the distance from any point to that plane. So that's the difference between what we're doing here and what we did with regression back in Unit 2. Okay. These V's are called the principal components of your data set. They're the directions where you have maximum variance in your samples. Okay, is this making sense so far? Okay, so we're going to derive it. It's going to take a few slides, but we'll encounter a number of principles which are really important, and you see them in other courses and other problems. Okay, so there's going to be 2 steps in our derivation. First, we're going to fix the dictionary at an arbitrary value b, and for that fixed dictionary, we're going to derive the optimal coefficients. That's easy. The hard part is optimizing the dictionary itself. Okay, first step, optimize zi's. So we have, for a fixed dictionary, we essentially have, remember this is our cost. Now let's say b is fixed, and I'm just minimizing this with respect to, let's say, z0. Do I care about the sum? No, I only care about this when I equals 0, right? So I just have a least squares problem for that particular zi. So I basically have this. This is my problem. Okay, so have we seen this before? Yes. How was it written when we saw it last? What was this? Y minus a beta, right? Y minus a beta. That's how we wrote it. So the solution is the same, it's just that the notation has changed. Now y became x, a became b, beta became z. But otherwise, it's the same equation as we saw before. So you guys have seen that derivation. We're not gonna repeat it again. Now we actually know for any fixed beta, we choose this is the optimal z hat I. So that's done. Now let's plug that optimal z hat I back into this expression. And then we get this expression here, which is a bit more complicated, given that our objective is to optimize b. right? How do I do this? B is it's in there in a convoluted way. It's inside this matrix inverse and all that. So how do we actually do this optimization? So that's what we have to work on for a number of slides. But that's our objective. And so essentially, I'll just lead you through a number of tricks that you can use from linear algebra. Like I say, these tricks are seen in many other problems. So the very first thing is, let's write this in a little simpler way. Right now we have 2 xi's. Let's just reduce that to 1 xi by putting in this identity matrix. And now we have this one big matrix, I minus this stuff. We're going to give this a name. I'm going to call this PB perp. This is what we call an orthogonal projection matrix. So let me talk a little bit about projection matrices. How many of you guys have seen projection matrices? Okay, so the idea of projection geometrically is pretty straightforward. If I have, let's say I can create any point in this plane, and I have some point that's outside the plane here, or maybe if you consider this the origin, then this we could say is a vector outside of this subspace. How do I find the closest point in the plane?
The orthogonal direction from the plane to the point.
Right. It's exactly. So, why is this orthogonal? Well, I don't know. Like, kind of geometrically, you can imagine, like, if I have some candidate point here, and I look at the distance here, and this is not a right angle. That means that I can move it a little closer, and I can move it closer and closer and closer until it's sitting here, and the error is orthogonal. And if I try to move it in any direction from here, that error vector, the distance from here to the plane, will only get larger, right? So this is the best it can be, is when the approximation error, the difference between x and the point in the plane, is orthogonal to the plane. So I think you probably have seen that in different forms throughout different classes in the past. So in terms of linear algebra speak, the way you describe this is you talk about a subspace. A subspace is basically, you can say it's a set of linear combinations. So here I have a tall matrix B, and I have a short vector Z, and I can think of this matrix vector multiply as this column times this scalar plus this column times this plus this column times this. So this is really linear combinations of the columns in B. And what we're saying here is I'm going to consider all linear combinations. So I'm going to allow Z to be anything. And that means that I get a subspace, which in this case, for this particular picture, B would have 2 columns, B1, B2. And now you're saying from here, you can make any linear combination of those 2 columns. So you can make any point in this plane, but you can't make any points outside the plane. Okay, so that's what a subspace is, defined by the column space of B. These columns are the things I'm using to create my space. Okay, so that's the idea of this subspace. So when we talk about orthogonal projections of this vector onto this column space, we can write them like this. We just sort of discussed this informally. X is the approximation, which lies in the plane, plus an error. And we just said, kind of intuitively, this error should be perpendicular to that plane, or perpendicular to that column space. X hat is in the column space. So it turns out that you can compute these things. If I give you this X, I can compute both X hat and E using these matrices that are called projection matrices. In particular, these are orthogonal projection matrices. And the way that they look, the orthogonal projection matrix, the one that projects B onto the plane, has this form. B transpose B inverse times B. And the one that is orthogonal to that is just I minus this other guy. So these are these very special matrices that do projection for us. And they have 2 properties, and really only 2 properties. They are symmetric, meaning P is equal to its transpose, and they are idempotent, which means P is equal to its square or cube or fourth power. So the way we can understand idempotency is to think of this matrix not as just a matrix, but as an operation that we multiply a vector by this matrix. That's like doing an operation to the vector, right? For example, if I start with this vector and I multiply this times PB, it projects it onto the plane. That's what this matrix has done. It's moved this down to here. What if I take that point in the plane and I do another projection into the plane? Does anything happen? No. So you can see why this is the same as this. Because this would be like first projecting x into the plane and then taking the result and projecting it again into a plane, which is the same as projecting into a plane and then not doing anything. So that's where you can understand idempotency, how that kind of makes sense with projection matrices. Okay. So any matrix you construct with these two properties will basically be a projection matrix associated with some subspace. Another interesting point, which we'll use in the future, is that when you look at the eigenvalues of these matrices, you find that PB has R eigenvalues equal to 1, and all the other eigenvalues are equal to 0. So this R, again, is the dimensionality of the subspace. In this case, it's two-dimensional. Then PB perp is the complement. It has R eigenvalues equal to 0 and all the other eigenvalues equal to 1. So these are sort of interesting properties of these projection matrices. Okay, so that's essentially what we have here. We have an orthogonal projection matrix. You can now understand geometrically what this means. We take xi, which is outside of the plane, and what does multiplication by PB perp do in words? Or in terms of this picture? What does it give us? It's the error. PB perp is the error, right? So essentially over here, if I have this point and I multiply this by PB perp, I get a vector. It's at the origin, but basically if this is the origin, then that vector is like that. I get the approximation error for that particular sample. If I do to this, I get its approximation error. So it just gives me the approximation error. And now you can see, well, of course, that makes total sense. The whole point is to minimize RSS, right? So if this is the sum over the square 2 norm of the projection errors, that's what we're minimizing. Okay, so essentially PBXI is a projection error. PCA is just choosing B to minimize the sum squared projection error. Okay, so this is the problem we're working on now. Okay, so questions on where we are? Okay, so now we just have to do a bunch of linear algebra tricks to deal with this. This proof is the shortest I could find of all of them that I've seen. Okay, so we're going to give this cost function a name. We'll call it JB. And as we see above, this is how it's defined. So the very first thing we can do to sort of proceed is recognize that if you have a 2 norm, that's like x transpose x, right? Squared 2 norm. So we can do that with this quantity. So this is like that part, and then the transpose part is this. Okay. Now, PB perp transpose by symmetry is the same as PB perp, right? So we can get rid of the transpose. And then I have PB perp squared, which is PB perp. You can get rid of one of them so that I get this. Okay, now the trace is a super useful quantity in some cases. This is one of those cases. This is a scalar. The trace is defined if you take a matrix and you want to know what is the sum of the diagonal components of that matrix, that's the trace. So if this is a scalar, that means the trace does nothing to the scalar, right? Because you can think of it as a 1-by-1 matrix. So we can just take this scalar and put a trace on it because that does nothing. But once the trace is there, we can use this wonderful property that applies inside a trace, that A trace of A times C is trace of C times A. You can swap the order of any two matrices in a trace. So this is amazing because, as we know, without the trace, you can't do this, right? Matrices don't work that way. But inside a trace, you can. So what we can do is we can move this one to the end. So that brings us over here. Next, the trace is a linear operator. So that means we can move the sum inside the trace. In fact, this is another linear multiplication, so we can move the sum all the way through and have it over here. And finally, we can sneak in a 1 over n here, as long as I put an n on the outside, and that gets us our sample covariance matrix Q. So here we have n times the trace of this orthogonal projection operator times our sample covariance matrix. And this is where we get the properties about sample covariance matrix. That's why all this stuff depends on the sample covariance matrix. Okay, any questions so far? Okay. So a few important facts about the sample covariance matrix, any sample covariance matrix, is that it's positive semi-definite. So what does that mean? It means for any vector x, you can dream up x transpose q times x, that's that quadratic form, can never be negative. This is what it means for a matrix to be positive semi-definite. We care about this because when we have a positive semi-definite matrix, then the eigendecomposition has a very particular form. Essentially, you can take that matrix and you can write it conveniently as a product of three different matrices. V, first of all, is an orthogonal matrix. That means that all of its rows are orthogonal to all the other rows. All of its columns are orthogonal to all the other columns. They all have unit norm, rows or columns. So you have these really convenient properties. V times V transpose is I, V transpose times V is I. That's what's special about V. Then lambda is a diagonal non-negative matrix. It's a diagonal matrix where these are the elements on the diagonal, and those guys are all non-negative. Okay, so whenever you have a positive semi-definite matrix, you have this. And so let's convince ourselves that Q really is positive semi-definite. So let's start with this. This is what we need for the definition. Let's substitute in the expression for Q. And now we can use linearity to move the 1 over n and the sum out. And you get x transpose times xi. And then you get xi transpose times x. But notice that this and this are really the same, right? Because these are scalars. This is a scalar. It's like a row times column. This is a scalar. And I can always transpose a scalar, right? Because transposing a scalar does nothing. And if I transpose this, I get this. So really these are the same, so we can just write once squared. And now you can see that this thing, a squared quantity can never be negative. And I have an average of squared quantities, so that can never be negative. Okay, so we've hopefully convinced ourselves that this really is positive semi-definite, and that it is, and so that allows us to use this decomposition. Okay, so what we have to do next is basically this is the problem that we're trying to solve. Minimize this n trace PB perp Q. So minimize n trace PB perp Q. So back almost 100 years ago, it was proven that to minimize this, it's enough to take the R principal eigenvectors of Q, meaning you search through the columns of V, you find the ones that correspond to the largest eigenvalues, you construct a tall matrix with those guys, and that is your optimal B. Okay, so let's see if we can prove this. Any questions on where we are? I know it's pretty heavy for linear algebra today. Okay, so this is our objective, minimizing this. So now we can maybe unpack this PB perp. Remember, that's I minus PB. And if we have that, we can multiply this out. We get Q minus PBQ. Those are inside a trace. Trace is linear. So we can have this minus this. And if I'm optimizing B, I don't have to worry about this. Forget about that. And if I'm minimizing this guy, because of this minus sign, I actually want to maximize this. So we'll call this a cost. We'll call this a utility. So this utility is what we want to maximize. So now we can use our eigenvalue decomposition. We plug that in for Q. We can use our trace property again. Then I can move this V transpose to the front. And now we get an interesting situation. So this is some matrix. I'll draw it out. Some matrix. This second one here is a diagonal matrix. And what we want is to compute the trace of their product. Okay, so when you think about taking this diagonal matrix and multiplying it times this full matrix, and then looking at the diagonal elements, let's think what happens. So when I take this column and multiply it times this matrix, it recovers this column, right? Because this just sort of selects the first column of this whole matrix. And so that means that when I look at the top left column in this product, it's just the top left column of this times this. Now, when I look at the next element, I look at the next element, let's see. So this element, that is going to be this times this, but I'm going to do this times essentially this. So it's going to isolate this one quantity. So that means that essentially I don't need to know any more than the diagonals of this matrix in order to compute this trace. All the off diagonals of this matrix they're not going to impact this quantity. So what we're going to do is we're going to call the on diagonal elements of we're going to call these diagonal elements alpha j. The alpha j is going to be the jth one. So this is this matrix looking at the diagonal elements, and realize that the trace is going to be this guy times this plus this times this plus this times this and so on. So we have the alpha j's times the lambda j's. These are the lambda j's. So we're just summing up those scalar products. Okay. So does that sort of make sense? Another thing we can use is when you look at these alpha j's, essentially they are, so to compute, let's say alpha j, you're going to take the jth column here, the jth row here, which is the same as this column, it's just flipped around, and you're going to multiply those with this in the middle. So that's this particular form you have. And it turns out that, remember, this guy has eigenvalues that are either zeros or ones. If I multiply that by these unit norm v's, I'm going to get answers that are somewhere between 0 or 1. They can never be outside that range. So that's an interesting property of the alpha j's. They're numbers between 0 and 1, never outside that range. And there's one more interesting property, what happens when we sum all the alpha j's. It turns out when you sum them all up, you get R. So let's try to prove that to ourselves. So the sum of these alpha j's, that's the trace of this matrix. So now we have this trace, so we can move V to the left. Now we can use the fact that V is an orthogonal matrix, so this is identity. So essentially that goes away. We just have the trace of PB. So what is that? Let's plug in the definition for PB. It's that complicated thing. However, because it's inside the trace, you can move this to the left to get this nice expression. And now we see that this will multiply this to turn into the identity matrix, because this is just this times its inverse. And finally, this is an identity matrix with R. It's an R by R matrix, so when I sum up the elements along this identity matrix, I get R. Okay, so we're almost done. We have this interesting optimization problem that actually no longer involves any matrices at all. So we want to find some alpha R's, and these alphas are between 0 and 1, and they sum up to R. We want to choose them to maximize this. So these lambda j's are fixed. Got them when we did the eigenvalue decomposition. We want to design the alpha j's to maximize this. We can actually think about this as a resource allocation problem, as a problem that we could face when we go to a store and we go shopping. So we can think of these alpha j's as some purchasing variables. J is going to be the jth item in the store. We're going to purchase between 0 and 1 of every item. So no less than 0, no more than 1. And we have our total budget, when you sum up how many different units we can purchase, it's total of R. So there's D items in the store, but we can't buy one of every item. We can only buy R total. And finally, the lambda j's you can think of as a reward for buying the jth item. So this tells us, this is the reward for the jth item. This is how much of that reward I get. It's how much of that item I purchase. And this is my total purchases. So basically, I have this budget. I can buy between 0 and 1 of every item. I can buy a total of R when I sum up all my purchases. And I know which items I like. I have ranked these lambda j's from large to small. So lambda 0 is my favorite item that gives me the biggest reward. Lambda 1 is next, and so on. So what do I do when I go to the store? Right? I can buy 0 to 1 of every item, and I have a total budget of R. And I know which items I like. What do I do? Buy the items I like. Buy one of each, right? And buy none of the remaining D minus R items. That's it. Purchase that's most rewarding is 1 unit of the R best items. So in math speak, that would be alpha j is 1 when j is 1 through R. That's because we already ordered them from large to small. And 0 when j is any number R plus 1 or above. Okay, so now we know what the optimal alphas are. Remember that, back to the linear algebra, this is exactly how those alphas are constructed. And so the way that I do this is if I construct let's see. So yeah, so this is how the alpha j's are defined. And basically, if we construct these vj's as the principal eigenvectors of this matrix B, then it turns out that the alpha j's we get satisfy this exactly. Let's see, we sort of saw this. We know this is true. Let's see, how do we get this exact statement? How do we get that exact statement? Okay, I'm blanking on the very last step, how to convince you guys that this is true, that this is true. Let's see, I guess we would need to go back to this matrix. Okay, somehow I'm blanking on this last step, but I apologize for that. So anyway, this is essentially, we can get these alpha i's by choosing B this way. Oh, that's right. We have to construct B this way. And then when we construct B this way, what happens is, this is essentially the projection matrix onto B. So it's like we're saying the subspace is going to be defined by these various V vectors, and then this is like a projection onto the plane. So these VJs are already in the plane, so when you project them, you don't change their length at all. Okay, so anyway, so this is how we can prove it. And then finally, just to summarize, someone is giving us this center data. We essentially compute the covariance matrix. You can actually do it in matrix form this way. Each of these rows of X are data samples. You compute the eigenvectors. You stack the principal ones in this matrix, and this is how you can approximate your xi's. Okay, so we saw these pictures before. Okay, so the last thing we'll do today is talk about how do we quantify the performance of PCA versus rank. We have this idea that as the rank goes down, approximation gets worse, and so it's important to know like how bad it's going to get. So we can use a technique similar to linear regression. For linear regression, we use R squared. We define it as 1 minus RSS over number of samples times the covariance matrix, or the covariance for our targets. For PCA, we use something almost identical, except since we don't have targets, we replace that with the total energy in our signal. So trace of Q is like the variance of all the features summed across the features. So it plays the role of that. So this is just the proportion of variance. This is the definition. This is a quantity that can go up to 1, because the best we can do is RSS is 0, where this is 1. So that's our goal. Typically it's some number less than 1. So we can look at this in terms of the eigenvalues themselves. So what we can do is we can look at the denominator, R trace Q, plug in the expression for Q, move this V back here, that will cancel with this other one, and now we have N times the trace of lambda, or N times the sum of the lambdas, which are along the diagonal of this lambda matrix. On the other hand, the RSS, if you remember, this was the cost that we were working on. So this is our RSS here. And on that page, we derived this, and N trace Q is as above, it's that. And then this other thing here, on that previous page, we derived that this expression is this. And so now you can see this is summing up all the eigenvalues from 1 to D. This is subtracting the ones between 1 and R, and what you have left are the ones from R plus 1 to D. Okay, so that's the numerator. This is the denominator. So here's the proportion of variance down here. The value 1, we're going to write 1 in a fancy way. Then this, we said we write it like this. And we wrote the 1 in this way so that we can have the denominators equal, so we can add those two terms. And now you can see the top is going to be the sum over all the j's minus the sum over the last j's, giving us the sum over the first j's. So finally, this thing we care about is directly proportional to all the energy from the first R dimensions divided by all the energy from all the dimensions. So it's just a ratio, and you can see that as R increases, this gets closer and closer to 1. As R decreases, this gets closer and closer to 0. So overall, this quantity is something between 0 and 1. Okay, so that's it for today. Next time will be more fun. We'll get to see this in action. We'll get to see a bunch of cool pictures and examples and stuff. So, sorry for all the linear algebra. Are there any questions on anything we did today? Okay. Yes.
If I get RSS equals 0, let's say reducing from 3, d equals 3 to r equal 2, could I interpret as there is a plane that can put
Yeah.
all the data in that?
Exactly. All your data is already on a plane, so you're free to take away one dimension out of your representation. You have lost nothing. So this works well when your data is really concentrated in certain subspaces and there's not much in other subspaces, and you can do this without losing much. Yeah, that's exactly the idea. And it's true for some data, it really does work that way. And as we'll see with faces, it works pretty well too. Okay, great. We'll see you guys on Wednesday.